Hello everyone, welcome back to the online video lectures on medical imaging. This will be an introductory lecture about medical imaging, and of course this will be followed up by maybe a couple of more lectures about some of the introductory material about medical imaging. In this lecture we will ponder on some of the basic details about medical imaging. Then we will also take a look at different historical milestones in medical imaging, different imaging modalities, and a classification of these modalities. This will be also finally followed up by looking at the notations or representations that are used while viewing the medical images. Let us start with the question, why medical imaging? So take a pause here, pause your video and think about it, and note down few points on why you think medical imaging is required in the first place, and then you follow up this video. If you go back around 400 years back to the human history, the only way you could take a look at the anatomical structures of a human body is through post-mortem, right? Fortunately, this is no more the only way to look at things. If I have to answer why medical imaging, the first point would be to see inside the body in a way that is less invasive or completely non-invasive. What I mean by that is sometimes you may send something inside the body to view whatever is there. So that's less invasive. That's what I mean there. And completely non-invasive means, it's completely non-invasive. If you look at the earlier picture and think about it in bit more detail, what you can observe there is structural information, or you could also call it as anatomical information. But that's not the only information which you could obtain these days. You could obtain information about the metabolic activity of various structures of the body. You could get the functional information on which part of, let's say, the brain corresponds to which functionality, and also the molecular activities, right? This is one example of the kind of advancements, scientific advancements that are happening. Say, for example, this is the magnetic resonance image, also known as MR imaging, something taken at, let me play a video of it meanwhile while discussing about that. So this is, I guess this is done at 100 microns level. You could get the precision using MR imaging, which is non-invasive. This is done by Massachusetts General Hospital, MGH, and even for our routine checkups of MR imaging, you would get resolutions of the order of millimeters very comfortably, 1 mm, 0.5 mm. These are quite common resolutions that you would get with MR imaging. So that's the kind of advancements that have happened over the years. Let's try to think about another important aspect of medical imaging. In the first place, how does an imaging work? In other words, how do you get the details that are there inside using an imaging? So to understand this question, let's think about a simple camera, normal images that you take with camera, and let's see how you obtain an image there, and that would help us to extend the same on, in general, how medical imaging works. Let us think about how we acquire an image. Okay, to understand this, let's think about how our digital cameras would work. Of course, what is the first ingredient is you should have a source of light for it. Okay, let's why not draw the sun? Let me entertain you with my drawing skills as well. Okay, you have a source of light, and then let's say you have an object for which you want to find out an digital image for that. So what would happen now? This light, there is a source, or let me call it, signal. Okay, and there is an object to be imaged, right? And from this signal, for example, if this is light, for example, a visible light, let's consider here, that falls on this body. or object. In our normal digital image cameras, what would happen? The light from the object would reflect, and so there is a phenomena of reflection here. The reflected light, you will have a an array of sensors that would detect the intensity of light. So this reflected light is falling on this, so you have an array of sensors here, right? And depending on the light that is falling on it, you get the image of that. This is what happens roughly in case of our usual digital images. Let me generalize it from the visible light to any signal as such. This could be okay. So there is some signal which falls on the object and reflects, and there are sensors that could capture the intensity of those signals, right? And should it be always reflection? Not necessary. This could also be the light that got transmitted. Okay, so here reflection, it could have been transmission as well. And then you again here you have an array of sensors that could detect the strength or the presence of that signal. So you could have here the sensors. So you can see here there could be the transmission imaging. So if you are getting this image through this transmission, that's one way. Through reflection, there is another way. And of course these are not the only ways. There are other ways which we would now write it. So the first category of methods, we are going to refer to them as transmission images that are obtained by sensing the signal that got transmitted through the object. So that's we would refer to as transmission imaging. And of course here that's radiographic imaging. That name would become more clear to you as we move on, but for the sake of completion, let me refer to it as radiographic imaging. Okay, and another one which you had already seen now is like what happens in a visible light, you could call it as reflection imaging. I don't know when A comes why it gives a peak there, some issue with the pen. Okay, anyways, reflection imaging. So this we would be more talking here about ultrasound imaging. That's what we would take a look at here, ultrasound imaging, right? And we will also take a look at two other types of imaging as well. One is referred to as emission imaging. Emission imaging, okay, and this, to be more specific, we would be looking at nuclear medicine. This is another category of imaging modality that we would be looking at, or a group of imaging modalities for that matter. And also the fourth one, we would look at magnetic resonance imaging. This is also referred to as, I'm sure most of you would have heard about it, is MRI, magnetic resonance imaging. So we will also see some of the key historical milestones in each of those imagings. Let us start with transmission imaging. As I mentioned, we refer to it as radiographic imaging as well. This is what I'm sure, at least with some of these modalities, most of you are familiar with. Okay, for example, X-ray imaging is one of the initial and one of the key imaging modality that can be grouped under transmission imaging. Again, if you want to classify transmission imaging into further categories, one class of methods you could put under projection radiography and another under computed tomography. Projection radiography means you are projecting a 3D object onto a 2D plane. It's also referred to as planar radiography also in some textbooks. Another one is computed tomography. This again we would discuss all these things in more detail as we move on in this course. This is a very introductory level discussion here. In computed tomography, you will get it in the slice wise information. So you have 2D information at different levels of z value. If you think the object height is in the z is representing the height, okay, and then these are the slices that you have. You will get multiple slices, okay. That's why this is a 3D information. So these are the, and tomography, that's why it is referred to as computed tomography. So essentially you will there do multiple projections, not just a single projection, multiple 2D projections of the 3D object, and from there you will be able to mathematically reconstruct the object in 3D. We will anyway discuss that in more detail as we move on in this course. All I will do in this lecture is just to introduce you to the names of these modalities, and as we move on we would discuss in more detail about some of these modalities. The first set of methods under this is what you use for routine diagnostic radiography, right? And X-rays, fluoroscopy, these are the, and there is another thing called as motion tomography. Although there is the word tomography, it's not really 3D. You would just look at the motion of it as a 2D projection, and that you will see it over time. All these imaging modalities fall under this routine diagnostic radiography. As I mentioned, your source is X-ray. Whatever got transmitted through the object and whatever is remaining, based on that you will figure out what the object is. So basically X-rays you use it, but here the sensor, whatever is there, could be either a film or you might digitally record it. So earlier in the beginning days, you have a film that is sensitive to the strength of the X-rays, okay. Based on that you will get the image. It is an X-ray sensitive film. On the other hand, if you are using in all the above mentioned imaging modalities of X-rays, fluoroscopy, etc., if you are recording them digitally, then the same thing you would call it as digital radiography. It's important you know these names so that you will know to which kind of category they fall into, and based on which principle they are working. Another one, angiography. Again, if you have elders in your home or in your relatives, you might have heard that if there is any problem with the heart, they'll go for an angiogram, okay. That gives you the this is again uses X-rays. It's a 2D image, but it's some over time, and it will give you the information about the blood arteries and blood vessels. That's again an X-ray imaging specialized for imaging the blood arteries and blood vessels. Another one, neuroradiology. This is again specialized imaging system, X-ray based imaging system, specialized for imaging the skull and the spine. Another one, another specialized equipment referred to as mobile X-ray systems. So in the operation theaters are to take X-rays in a place that are where the patient cannot come, but the machine has to go. That's where specialized machines are referred to as mobile X-ray systems. Another one, this also mammography. Most of you would have heard this name. This is particularly used for the diagnosis of breast cancer in women. This is a specialized X-ray based system for breast imaging. Okay, these are different kinds of things, but the principle of all of them is more or less same, except this is specialized to be very accurate for the diagnosis of different structures. Okay, we will anyway come back to some of these modalities later in the latter part of our course. And with that, X-ray imaging, so this is what I am referring to as X-ray imaging. So all of them are X-rays, okay. Although the latter second part, computed tomography, is also another classification of X-rays, that 3D one usually referred to as separately rather than calling it as simply X-ray imaging. I'm sure you all know from your +2 that William Röntgen, is considered as the father of X-ray imaging. You all know that he has accidentally found in 1895 while experimenting with these X-rays that these rays would pass inside the body, and that's why you could see through the body. The first clinical use of X-rays happened quite fast in 1896. Important thing to notice here is it is very unusual that a person is given a Nobel Prize within 4 to 5 years of discovery of a phenomena or a principle. That should tell you already how important or significant this discovery has been. As I mentioned, this is also referred to as planar radiography. You could use it to take static images, or you could also use it to take dynamic scans. By that we mean images taken over time. For example, to understand the blood arteries and blood vessels, you may go for dynamic scans. Okay, so with that we will move on to the another category of transmission imaging, CT imaging. Again, this has been a very important invention in medical imaging. This is considered as the next important, very important invention after X-rays. You could see discovery of X-rays happened 1895, and it took around quite some time, 1972, so around 75 years after that, on Godfrey Hounsfield, he has come up with the first computed tomography scanner. Mathematical framework that is required for the image reconstruction of this X-ray based image reconstruction in 3D. This mathematical framework has been developed by Alan Cormack a decade earlier, so sometime in 1960s, and this is again very unusual that within 7 years of development of this first computed tomography scanner, both Hounsfield and Cormack shared a Nobel Prize, and this time this is in medicine. Earlier one was the first Nobel Prize in physics, okay, Röntgen, and this is the Nobel Prize in medicine. As I mentioned, development of CT scanner is considered as the most important development in terms of in the medical domain after the discovery of X-rays. Next we will move on to another category of imaging modality. This is referred to as emission imaging, and in particular we will be talking here about nuclear medicine. Okay, by the way, I am keeping some images here. Later you pay attention to that and explore about them in more detail. Anyway, we will come back to some of these images little later in our course. You could notice here around 1896 X-rays have been discovered, and inventions are going and further developments are going on there. Around the same time, you also know it from your +2 chemistry courses that Henry Becquerel discovered the radioactivity around 1896. But initially the application of that when it comes to medical imaging was for treating the cancer. That's the initial one, but it's not for the diagnostics. You can notice here that within the next 25 years, the concept of using this radioactivity to study the physiology was introduced by George Heavisey. You could notice that while you are using X-rays for understanding structural information of the body, different structures in the body, this nuclear medicine is used to understand the metabolic activity of the body or to study the physiology of the body. So they are in a way complementary. And 1949, the first imaging system has been developed by Benedict Casson. This is also referred to as gamma camera, okay, or uses gamma camera and rectilinear scanner. The modern day camera, which has been developed by Hall Anger at UC Berkeley. On his name, this camera is also referred to as Anger scintillation camera. This has been developed by 1952. Just like we discussed about different kinds of imaging modalities that fall under X-ray based imaging, here also 3 important imaging modalities that are in practice are scintigraphy, then SPECT means single photon emission computed tomography. So computed tomography, from the word you could already guess that this gives you a 3D image. And then PET image. So this is positron emission tomography. So the basic principle is like this. Whatever they are referring to here as radioactive tracer, a radioactive material has been injected or ingested or inhaled into the body. The radioactive material will be emitting the radiation, and that emitted radiation is analyzed and sensed in order to understand the metabolic activity of various structures in the body. This is a very brief discussion about nuclear medicine. If time permits, let's discuss in the due course of time about at least positron emission tomography. Again, I am not explicitly mentioning here about the important historical landmarks in terms of the Nobel Prizes. For example, Henry Becquerel and George Hevesian, both of them, and there are few other Nobel Prizes also. That means very landmark discoveries have happened here. So with that, let's take a look at another kind of imaging, reflection imaging. So this is where you are sensing the reflected signal from the object. Under this, we are discussing about ultrasound imaging. This again, most of you would have been, I'm sure, will be familiar with this. Essentially, it uses a transducer that converts the electrical signal into acoustical signal, and that transducer is used to generate repetitive bursts of high frequency sounds. This will be kept on the part of the body which needs to be scanned or imaged, and what you would be studying then is the time of return of these pulses and also the intensity of these returned pulses. These are the two things that you would be studying to infer the location as well as the strength of the, so the composition of the structure, let's say, or the type of the structure, if not composition. Those are the things you would be inferring. Okay, this again we are not going to look at in detail for now. We just want to get a broad overview of different imaging modalities here. So we will not go in detail right now, but the examples here for your reference are, there is something called as an A mode imaging, then there is a B mode imaging, M mode imaging, Doppler imaging, and nonlinear imaging. These are 5 important examples of or specializations of ultrasound imaging. Yeah, I would request you to Google those names and see in more detail about them. Okay, with this I will skip from that to another important imaging modality, which is a more recent imaging modality than the ones that we discussed so far, and this is referred to as magnetic resonance imaging. This started in 1945. Bloch and Purcell, these are two professors from 2 different universities. There are again some more important historical landmarks happened before this. I'm skipping them, but these are the ones who had given a first mathematical basis for nuclear magnetic resonance. This work again within no time, almost in 7 years, has been awarded a Nobel Prize in Physics. The next important historical landmark here is in 1963, Richard R. Ernest, he has invented Fourier transform based nuclear magnetic resonance. So this is the one which is used to understand the chemical composition or the molecular, what are all the molecules are there in a given substance. So this is in chemistry, it is widely used even today. So this has been invented by Richard R. Ernest in 1963. Again, this is awarded a Nobel Prize in Chemistry in 1991. When it comes to imaging part, so far earlier it is used to find out what are all the molecular structure of a given material. But as far as imaging is concerned, Paul Lauterbur and Peter Mansfield, they have independently suggested the use of magnetic resonance phenomena for capturing the medical images. This is again another Nobel Prize. This in medicine now, or in physiology they call also, in 2003. If you notice, the earlier one, X-ray based imaging, would give you the structural or anatomical information. Nuclear medicine would be giving metabolic information. And when it comes to MR imaging, there are again many other modalities within MR imaging modalities, submodalities you can call them. Standard MRA, echoplanar imaging, MR spectroscopic imaging, functional MRI and diffusion MRI. They will give the functionality information, metabolic information, as well as the structural information, depending on which kind of submodality of magnetic resonance imaging we are using. Well, these are not the only historical landmarks in MR imaging. There are, before that, even there are some other important breakthroughs that had led to the development of this magnetic resonance imaging. I'm just outlining them in the slide. You could come back later and look into them in more detail. Let us now take a look at into these modalities from the electromagnetic spectrum point of view. So you could see here, for example, we know in terms of energies, if we start with the visible spectrum, above the visible spectrum you have ultraviolet spectrum, right? UV rays, X rays and gamma rays, and below that you have infrared, microwave and radio waves. So can you think of any imaging modality that uses the light which is there in the visible spectrum? That is endoscopy. Some of you might be already knowing about it. It's like a small camera, visible camera is sent inside in endoscopy, and then they will be taking a look at how various organs are there, right? That's in the visible spectrum. Now if we move on to the spectrum on the higher energy side, okay, X-rays we have seen, that's all the computed tomography and then X-ray based mammography, and then the chest X-rays, all these things which we have discussed uses X-rays, and nuclear medicine uses gamma rays. And on the other side of the spectrum, we have not gone into the details of MR imaging, but it is enough for the time being that to know that this uses radio waves. So from this you could already infer which are having a radiation effect and which are safe. So of course endoscopy is safe. In terms of radiation, there are no radiation effects. Similarly, magnetic resonance imaging doesn't have any radiation effects, and then X-rays does have radiation effects, and of course gamma rays also have radiation effects. So you could see here MRI on one. So this is kind we are looking at now. The energy is increasing as you are moving from left to right. Okay, energy E equal to h nu, you all know that. So energy is increasing means the frequency is high, that's why energy is increasing. So MRI on one extreme, endoscopy, and then radiography, CT, and then comes nuclear imaging. Okay, so with that, let's take a pause from these imaging modalities, and let me cover here about the terminology used while viewing 3D images in medical imaging. These are unlike the conventional images that you see. Now you need to look at a 3D image. So what the doctors or the radiologists, and of course we ourselves also will be looking in this course, are 3D images, some of them. So this, the way they are represented is, so one thing is called axial slices, another is coronal orientation, and another is sagittal. So these are the three directions in which you will be seeing 2D images. So essentially you want to see 3D. So for that what you do is, in fact, that information you see in three 2D images, if I could put it so. So axial is something, this like slice. So this is, for example, if you want to see the brain here, usually this is referred to as the axial orientation. Okay, so if you want to look at the sagittal, so if you are looking at from this viewpoint, okay, this is sagittal. Coronal is you are looking in this direction, so you are looking at slices in this direction. If you are slicing me in this direction, as you could see in those images, okay, that's, this is coronal, okay, this is axial, and this is sagittal. If you are looking from here, you are moving away, then that is sagittal. These are the three orientations that you would be looking at images. This is, for example, images in these three orientations. Another one to know is anatomical positions. These terms also should be clear to you. Most important things I'll point out here, the rest you go through it there. Anterior and posterior. So here this is called as anterior and posterior. So while a scan is captured, whether it is captured in this direction, as I mentioned, you are taking slices. So if it is taken from anterior to posterior, or posterior to anterior. So from front to the back, front is anterior, the back is posterior. Another one is of course left, okay, and right. And another important one is inferior and superior. Inferior is down and the superior is up. It is enough at least you know these things, anterior to posterior, and left and right you know already, and inferior to superior. So with that we will stop this introductory lecture. Let's continue this further in the next video lecture. Thanks for watching. See you in the next video lecture.